so we need to use some black mathematics. We need to play physicist. Good morning, fellow mathematicians, welcome back to another video. It's once again time for Papa Flammy's random week, and we are going to do some Newtonian mechanics today. Imagine this little scenario. This right here is you, the mass 1 boy, and this right here is, for example, meteorite Euler, mass number 2, and we are going to act like you. Boys are just mass points, little particles, and how long would it, you boys, take to meet somewhere in the middle due to your own gravitational attraction? That's something we want to derive today, and it's quite fun. It's quite a nice calculation, ending up with some interesting differential equations. So at first, let's take a look at our formulas that we've got here. So at first, imagine this mass number 1 acts on this mass number 2 with a certain force. This force right here is called the universal gravitational force. And it's denoted as follows. So we have this gravitational constant, m1 times m2, and also we are having this right here, r2 minus r1, but squared. That's nothing but this whole distance right here. We are going to denote it as capital R. So r2 minus r1 is just capital R. That's the distance between those two. And also, Newton's second law of motion states that there's also a reacting force from the mass 2 on the mass 1. So that's the same force like here, but with a negative sign. Keep this in mind. So that's something that holds. But what exactly is a force? For example, the force from this mass 1. It's nothing but the mass 1 times the radius 1, double dot. Mass times acceleration. It's nothing but that. Same thing here. So mass 2 times the acceleration. Radius 2, double dot. And that's a system of equations, and we can add them together or subtract them together, for example. So why not subtract this equation from this equation right here? That also means that we end up with, at first, what we can also do, I totally forgot that, we could divide both sides right here by m1 and m2, just to make things a little bit easier. So dividing both gives us this. So that's quite nice, and now we can successfully subtract them. So we are going to end up with r2 double dot minus r1 double dot. And don't forget, this is just the second derivative of r2 or r1 with respect to time. So we can rewrite this as the second derivative with respect to time of r2 minus the second derivative with respect to time of r1. And by the laws of differentiation, we can factor this differential operator out, so we end up with d squared t of r2 minus r1. Keep this in mind. And also we need to subtract this from this. So we have some common factors. We have g over this stuff as a common factor. So we have g over r2 minus r1, but the whole thing squared. Also we are going to end up with a negative sign here, so we can factor out this negative sign. And well, we are going to add m2 and m1 together. m2 plus m1. So that's all there really is to it. Now we can substitute a little bit. For example, we could call this addition of masses, capital M for example, for the whole mass of the system. And r2 minus r1, well, we have denoted this as capital R. So we end up with capital R double dot, so second derivative with respect to time of this distance r, equals to minus g times capital M over r squared. And we came pretty far on that already, but now it's going to get quite counterintuitive and hard, because this right here is a non-linear second order differential equation. And solving something like this isn't straightforward. There's no real recipe for solving stuff like this, so we need to use some black mathematics. We need to play physicist. I didn't know why I did that. Never mind. So let's denote this a little bit different. So we know that this is just d squared of r differentiated 2 times with respect to t. But don't forget something. We know that the velocity, for example, is nothing but this distance differentiated with respect to time. What that also means, that r double dot is nothing but dv dt. I hope you agree with me that this is true. Okay, nice. So we can plug this in and turn this second order differential equation into something first order nonlinear. So this helps out a whole lot. So we end up with dv differentiated with respect to time equals to minus gm over r squared. Just like I said before, we need to use some mathemagic. So we are going to multiply this dv over dt by a 1, because we can do that, that wouldn't change anything. But what exactly is a 1? Well, a 1, for example, is just the distance differentiated with respect to the distance. So this is dr over dr. And now we are going to use a theorem from calculus, Papa Schwarz, and we are going to just interchange this r and v up here, so the order of differentiation in that case. So interchanging this to dv dr, dr dt, this also looks like the chain rule. This helps a lot, because we know what dr dt is, that's just the velocity, and we end up with a formula saying that the velocity times dv over dr is nothing but this term right here. That's nice, because we know how to solve that. That's really easy to solve now, because we can integrate both sides with respect to r and putting in some upper and lower bounds. So let's do this real quick. So differentiating this side with respect to r leaves us with v dv equals to, we can bring this factor minus g over m to the outside, so minus g over m times the integral going from 1 over r squared dr. All that we're missing are upper and lower bounds now. Let's do this. I can't really tell you how annoying this was just now, because my nose was itching all the time. I guess you guys saw that, and that was really confusing. I got rid of that little problem now. Okay, let's go ahead and get started. Just like I said before, we want to plug in some initial values. Why not look at the point of time when t is equal to 0? Maybe that makes things easier. So at the point of time, t equals to 0. What are the rules there? Well, at first we have some initial distance between those 2 points at the beginning. So that means r of 0 is nothing but, for example, some initial radius ri. And also, what's the velocity at the beginning? Without loss of generalization, we are going to say that v of 0 is nothing but 0, so they are not moving at the beginning. We are going to hold those boys tight. That's nice, we have all the information we need to plug in. So why not choose t equals to 0 as the lower bound? That means we end up with a velocity of 0 and also with some initial distance. And as an upper bound, why not choose some random velocity at some point of time, so v with respect to t, and well, this is corresponding to some random distance between those two masses, r with respect to t. And don't confuse yourself, those are just names, so you can substitute them by u. It doesn't quite matter, so don't confuse that here are r's up there. And integrating this stuff is quite easy. So on this side we are going to end up with v squared over 2 from 0 to v of t. Well, 0 is just 0, so we end up with v squared over 2. And on this side, integrating this is also quite easy. We are going to get rid of the negative sign right here, so that's great. And also we need to add a new power to this r right here. So this is going to be g times m times 1 over r in that case, from ri to r with respect to t. And we can plug those values in, so this is going to be g times m, and then we have 1 over r minus 1 over r initial. We can add those two together, that's also something we can do. So advancing those fractions by ri over ri and here by r over r, we end up with, let's put it here, v squared over 2 is nothing but g times m, and then we have ri minus r over r ri. Great. we have found a nice little formula for the velocity. All that's really left to do is to multiply both sides by 2, not equal to 0, and take the square root and see what we get. So we now have that v, which is just, don't forget what it is, this is just r differentiated with respect to t, is now equal to plus minus, and I'm going to leave both values of the square root right here. We are going to see in the end what's physically correct. Plus minus the square root of 2 times gm times ri minus r over r ri. Okay, great. And solving this right here is really easy because that's just a simple differential equation, first order. We know how to solve that. I have made a series on that. So I put everything here, and I want you guys to remember what our initial goal was. We wanted to find out an expression for the collision time. The thing is, this dt right here is in the denominator right now. So what we could do, we could integrate both sides with respect to t, that would be the mathematical way, and also we can divide both sides by this term right here, because we have to integrate with respect to r on this side later on. That's the first one. But we can also play physicists. What we could do, we could multiply both sides by dt, not equal to 0. It's a tiny, tiny portion of time. And also we can divide both sides by this term, not equal to 0. And then integrate both sides with respect to the certain variable. What that means, finally, is just that we end up with some dt being equal to 1 over plus minus square root 2 times g times m ri minus r over ri times r. So that's the first one. And then times dr. So that's the same procedure. You can also take the reciprocal on both sides and then integrate both sides with respect to t. It doesn't quite matter. There are many ways to do something like this. And now we need to integrate, just like I said. So integrating both sides right here will leave us with. It would be nice to plug in some initial values once again. So why not deal with t equals to 0 once again as the lower bound, so that we would get rid of some t value. So t equals to 0. What was the initial radius? Well, that was just ri. And we wanted to calculate our collision time. We're going to denote it by, I don't know, capital T with a little c as an index. And what happens to the radius, the distance between those two masses, when they collide? It's just 0. So that's nice. So we're going to get rid of two values right here. That's always good. Integrating this side is really easy. We're going to end up with small t from 0 to tc. It's just going to be the collision time. And what is this right here? Well, we can do some factoring out in that case. So what we can do, we can factor out 1 over 2 times g times m, plus minus the square root, don't forget that, and also this little ri right here, 1 over ri. So this is going to give us square root plus minus ri over 2 times g times m, times the integral going from ri to 0 of. And all we really have now is 1 over ri minus r over r. In that case, we can take the reciprocal, so we have square root r over ri minus r, integrated with respect to r. And integrating this isn't too easy. We need to do some manipulation, so why not introduce a new substitution? Let this whole term right here be, for example, u. I don't care what you call it. So let some u be equal to square root r over ri minus r. So this is going to be the interesting part. It's integration. You guys like integration. What that also means is that u squared is nothing but r over ri minus r. But bringing all of this into respect to u, when differentiating once again, that's going to be quite a mess. So let's do some algebraic manipulation. So we can multiply both sides by ri minus r. It's not equal to 0. So we end up with u squared times ri minus u squared times r will be equal to r. Well, we can add this term on both sides right here. So let's do this real quick. So this is going to be equal to r. Plus u squared times r. We can factor out the r in this case, so we end up with r times 1 plus u squared. Okay, that's nice. And now we can divide both sides by this term right here. So we end up with u squared times ri over 1 plus u squared will be equal to r. And that's nice because we can differentiate both sides now and see what we get. But at first I would like to do some more algebraic manipulation, because if you take a closer look, we can play around with this expression right here a little bit. So what we can do, we can turn this into u squared r times I, and now we could add a 0 and it wouldn't change anything. So what exactly is a 0? It's just ri minus ri. You will see in a second why I'm doing this. Over u squared plus 1. If you take a closer look, if we would factor out the ri on those two terms, we would end up with ri times u squared plus 1. So this and that is going to cancel out. We would end up with a single factor of ri and also this minus ri over u squared plus 1. So we end up with ri minus ri over u squared plus 1. So this simplified pretty nicely because we can differentiate this term right here pretty easily. It's way easier than differentiating this right here. No product rule or something. So let's go ahead and do this. So don't forget what 1 over u squared plus 1 actually is. We can rewrite this as ri minus ri times u squared plus 1 to the negative 1 power. And differentiating this is going to be quite easy. That means that dr, so differentiating this with respect to r, leaves us just with dr, will be equal to, that's just a constant, it's going to drop out. We have this negative ri, it's a constant, it will stay, negative ri. We are going to drag the minus 1 down and reduce the power by 1. So that means negative 1. And then u squared plus 1 to the negative 2 power. And now we need to take the inner derivative, chain rule. So that means the inner derivative is just 2u in that case, multiplying by 2u. So what's the derivative of r? It's nothing but minus and minus is going to cancel out. So we have 2 times u times ri over u squared plus 1 to the second power. That's quite a mess. But we can plug all of this stuff in and see what we get. So don't forget, this right here was our original expression. We have this, which is our u, so we have to multiply u by this thing right here. So that also means that our collision time is nothing but the integral going from... No, at first let's put those constants here. I totally forgot them. Plus minus square root ri over 2 times g times m. Okay. There we go. And now we have some new upper and lower bounds. If we plug ri into our r right here, we end up with ri minus ri. So that's 1 over 0. This is tending to infinity in the limit. So this is infinity. And if we plug a 0 into here, well, this is going to be 0 over something. That's just 0. So new bounds going from infinity to 0 in that case. And now we can plug all the other stuff in. So we end up with 2 times u, but squared because we have u times this chunk, ri over u squared plus 1, but the whole thing squared, du. That is quite a mess, to be honest. We can bring this 2 times ri to the outside, so let's do this real quick. Cleaning a little bit up, 2 times ri. And now we have this expression right here. And you see we have u squared plus 1 down here, so it would be great to introduce some new substitution with respect to some tangent or hyperbolic sine or something. So let's just say that u is nothing but tangent of something. Let u be equal to the tangent of phi in that case. If we differentiate that, that also means that du is nothing but secant squared of phi d phi. We are already defining stuff. Oh, defying stuff. Never mind. That's not funny at all anymore. So we can plug all this new information in, and we end up with plus minus square root this chunk right here, ri over 2 times g times m, 2 times ri. We have some new upper and lower bounds. It doesn't matter. I don't want to plug them in right now. We can plug them in the end. Okay, so what do we have here? U squared is going to be tangent squared of phi in that case over. Now we have tangent squared of phi plus 1, but the whole thing squared, and du is just secant squared of phi d phi. What is tangent squared plus 1? That is going to be the secant squared. But we have secant squared, which is going to be secant to the 4th power. So this secant squared and this is going to cancel out. So right now we end up with plus minus this whole chunk Ri over 2 times g times m, 2 times Ri, some integral, some upper and lower bounds we don't know yet, and then we are going to have tangent squared of phi over, and this right here is going to be just 1 over secant squared of phi d phi. And don't forget the definitions of this right here. Secant is nothing other than 1 over cosine, and tangent is sine over cosine. So that means we are going to end up with the sine squared all in all. Write it out, you will see that this is right. So positive, negative, Ri over 2 times g times m, 2 times Ri, integral going from, what do we have now? We are just having the sine squared of phi d phi. And now we need to integrate the sine squared. So the hardest part is done. I said in the beginning that it's not quite easy. So let's evaluate this right here. We could just use integration by parts for that matter. So using the DI method in this case, plus minus, and we are just going to deal with this part right here. This is our integral, I don't know, let's call it capital F, because I have an I here. Sine of phi will be differentiated, and sine of phi is going to be integrated. Integrating this is minus cosine of phi, differentiating this is just cosine of phi. Multiplying this together, taking the integral of this thing, is going to leave us with f being equal to minus sine of phi cosine of phi, and then adding this together, positive integral of cosine squared of phi. But what is cosine squared of phi? Don't forget your d phi in that case. Cosine squared is nothing but 1 minus sine squared of phi. So taking the integral of that, we can use the linearity to break this up into 2 integrals. I hope you see where this came from. And this right here is exactly our capital F, this integral right here. You see? So what we can do, integrating d phi, is just going to give us phi in that case. So we can add f on both sides because it's negative f. We have a negative sign here. So we end up with 2f being equal to, now we have phi minus sine of phi cosine of phi over nothing at the moment because we can multiply both sides by 1/2 right here. And this is going to give us the desired expression. Okay, great. So that was a standard integral. I rushed through it. Just take a piece of paper and try it out for yourself. It's quite easy to integrate. And we can plug all this information into TC. So the collision time is not nothing but plus minus the square root of Ri over 2 times g times m, 2 times Ri. And also we ended up with this result right here. Phi minus sine of phi cosine of phi over 2. One little thing, I haven't plugged in any upper and lower bounds at the moment, so why not substitute back? So I don't know what the values are. So let's substitute back, it's quite easy. Don't forget our u was nothing but tangent of phi. But what is the tangent? Tangent is just opposite over adjacent. So this is u over 1 in that case. Let's take a look at some triangle. That means we had some angle phi right here, and we have a u here and a 1 here. That means our hypotenuse is just u squared plus 1. So now we can calculate our values for sine and the cosine. So that means the sine of phi is nothing but opposite over hypotenuse, u over square root, u squared plus 1. And also, what is our cosine? This is just adjacent over hypotenuse. So cosine of phi will be equal to 1 over square root u squared plus 1. We can plug this in, so multiplying those denominators together will give us 1 over u squared plus 1, and we have this u up here. So all in all, the expression for our collision time is nothing but plus minus square root Ri over 2 times g times m, 2 times Ri, and also we are going to end up with phi is nothing but the inverse tangent of u in that case. So inverse tangent of u, and also we can bring this 1/2 to the outside and cancel those two out. So yeah, that would be better. So inverse tangent of u in that case, and then minus u over u squared plus 1. And we know what the upper and lower bounds are for the u case. This is just going from infinity to 0. If we plug in 0 into here, this is going to give us 0. If we plug in infinity into here, you can use L'Hopital's rule, for example. You are going to see that this denominator is growing way faster than the numerator in that case. So this is going to cancel out in any case. And also, the inverse tangent of 0 is just 0. And the inverse tangent when u approaches infinity is going to be pi over 2. But that's the second part of the integration, so it's negative pi over 2. And now you see why I kept both signs right here, because we are having a time on the left hand side, and time is always going to be positive. That means we are going to end up with a negative sign right here for the square root, such that this negative and this negative is going to cancel out. So what exactly is our final result? I'm going to put it here. So the collision time, all in all, is this whole chunk right here. So we are going to end up with square root Ri over 2 times g times m times Ri, and also we have times pi over 2. We can bring this together a little bit. 2 is nothing but square root of 4. So that's nice, we can bring it to the inside. So we have an a right here, and Ri is nothing but square root of r to the second power. We can bring it to the inside, so we end up with an expression for the collision time of being square root of Ri to the third power over a times g times m times pi. It's always crazy how pi pops up everywhere. And then we are done. So that was quite a lot of calculating. That's a crazy effort for a video. Told you guys I wanted to do something special, and this thing got requested. Totally forgot to mention this. I hope you did enjoy this video. Maybe I can verify this result with some experiment or something. Just put some initial value in here, and also don't forget capital M is M1 plus M2, so you know what the masses of the two objects are. And then you can calculate the time it takes for them to collide. I hope you did enjoy this little video. If you did, please like and subscribe and recommend me if you like. If you want to support me a bit more, link to my Patreon is in the description. And up until the next video, have a flammable day. See ya!